Hello, we are doing our cracking project. I am Tyler Andrews,
I'm Vincent Faragalli.
and we've been doing a little bit of the hash cracking slash matching using Kali Linux, mainly using Hashcat. We tested hashes, mainly MD5, SHA-1, SHA-256, and bcrypt. So essentially what we did, we created a file, we put our hashes in there, then created a hash of whatever was in our word list, and then matched the two. It did it for the entire word list, then, and that was using our different hash, uh, wow, I can't speak, our different hashes. So MD5, that took 12 seconds to crack the hash and matched it in the dictionary from our file. Then SHA-1 took 45 seconds, SHA-2, 256. 54 seconds. And bcrypt, we tried to crank it up to 11 on this one, see how long it could go for. That was 17 days. So that's what we found initially. I thought 17 days was going to be on the higher end when it comes to crack hash or hash cracking, but that was very wrong. So our progress since the proposal, we tried to move away from dictionary attacks. So we tried more the brute force slash mask attack. And in Hashcat, the brute force is outdated and it's been replaced with a mask attack. So if we had like a password length of 9, it would just, a brute force would just iterate through all 9 of those slots with, for example, if we have just lowercase, uppercase, and digits, it would be 62 to the 9th power, which is 13.54 quadrillion combinations. And if you were cracking hashes at like 100,000 or was it 100 million, I forget. I think it was 100 million per second. That would take about 4 years to actually go through that entire key space and try each and every password. So this mask attack essentially considers how humans will create passwords, and it kind of plans accordingly. So example, at the bottom here we have like password 123. It'll take password, and it'll flip around common letters, like example, the S's turn to dollar signs, the O to 0, then it might add like a year or a number on the end. So it tries things like that, and it's much more successful, and it speeds it up by like 100 times. So this reduces the password pool significantly. So instead, it's like this number of combinations for a 9-digit password instead of 13 quadrillion. So this is much more efficient. Then we try this attack. Did it with MD5. So this takes another dictionary word and then slaps a character onto the end and iterates through all those characters. We are using a built-in character set with the question mark A. So that's just all the lowercase, uppercase, numbers, and special characters. And it's not very significant when you get to 1 digit, 2 digits. Those are less than 1 second. Same with 3 digits. But once we start getting to 4, the computation time gets a lot higher. We hit 3 seconds, which is still nothing. And then we hit 5, which is 2 minutes and 54 seconds. That's a lot more. So it's definitely an exponential curve on this. So I did a little bit more testing. And these numbers are from my computer being able to crack 27.9 million hashes per second. So from here, we have some graphs. So we stopped here over at 5 on this left graph. So you can kind of see the longer the password, that's our x-axis. We go from 5 to 6, not much of a change. And then 6 to 7, it's a huge explosion of change with different MD5, SHA-1, 256 hashes. And I kind of made these graphs side by side just to compare, because the y-axis, it's in millions of minutes, which is kind of crazy. So yeah, so you can see on the left graph, it goes from 6 to 7, and you see the huge jump, but this is the same scale. Then 6 to 7 on the right graph, it's just flat. There's nothing. So with each increment of another character in the password, it just gets more, and more. Like 8 to 9, that's pretty much where you want to be with a password, because that's what, more than 1,000 million minutes. That's insane amount of time to crack a password. That's with SHA-256. So that's kind of the sweet spot when you trying to create a password. Here's that data for that. I initially wanted to put bcrypt on the far right here into the data, but as you can see, it would just blow it out of the water. Like everything on this graph would just look flat. So we just kind of excluded it for the sake of actually being able to show the data. But yeah, bcrypt with a password length of 5 up on this top row. That takes, let's look down here at years. It takes 1,495 years just to crack that password length of 5. So there's some pretty good hashing algorithms out there that are very resistant to this type of attack. And then I kind of went and tried the hybrid attack also. This is very similar to a mask attack that you can use a dictionary and then you would slap on more characters at the end or in front of it. But the difference between hybrid and brute force, the hybrid is only limited to the words that you put in the word list. Then it matches those instead of altering the words in the word list, like our password, where the S is turned to dollar signs. For example, if that's not in the dictionary you're pulling from, it's not going to be able to guess it. So this one is a little bit more simple, and it's not going to be as computationally complex. So yeah, very similar. So we have our character sets of just digits. It'll go 00000000001 and keep flipping through until it's all nines, and it'll combine that with a password. And yeah, again, tested it with MD5, SHA-1, 256 for the hybrid attack. And these were a lot longer than I thought they'd be. So simple MD5 hash with 5 digits plus a word list word was 20 hours and 33 minutes to actually crack that. SHA-1, 1 day, 1 hour. SHA-256, 1 day, 13 hours. So it's kind of the common curve that we see. More modern hashing algorithms, they just take longer to match the hash. And that was at 19.3 million hashes per second.
So part of the project we did last time as well is now that we know how to crack the hashes, how long it takes for each hash to be cracked, but how do we actually go about getting these hashes? What are the scenarios that we would need to crack them in the first place? Previously, we did it on a vulnerable machine, but that's kind of a really easy scenario and not very likely since getting a vulnerable machine is really hard to do. So I looked into two different things. The first one was getting hashes via Wireshark. So for this part of the project, I created a basic HTML web page. I use a Flash server for the reason that it does Python and handles HTTP requests and responses within a single file instead of having to have a bunch of dependencies. And on the left, you can see one of my machines is has that up, and I just took that from a previous project. And then on my main machine, I opened up Wireshark and started receiving what was going on the network. And I filtered for posts since that's what's happening when a password is entered. And then I went on my other machine and entered the username and password. And as the middle screenshot, you can see that Wireshark was able to read both the username and password, and you see that password is hashed. Now this one's pretty simple. You just take the hash and you put it through Hashcat. As you can see below, it's just password. This one was kind of basic of how to get the hashes more than cracking it, which was gone over earlier. So the next slide shows the second way that's an actual practical way that we, as either pen testers or hackers, how they get hashes, which is through a rubber ducky, which is a payload injection tool that looks like a USB, but it's actually a keyboard emulator. And it's part of the Hack 5 things, such as like a Wi-Fi pineapple, which other people have gone over before, and uses its own programming language through Payload Studio. So for this project, I created kind of a more basic script, which basically just when you plug it in, this is for Windows 10 only. It can work with other OSs, but I just don't want to program that. So this script specifically, it will copy the sam.back file in the system file to a personal server. What it mainly does is that it copies them to a temp file and then transfers them and then deletes the temp file. And this really only takes 5 seconds to plug in and run. So really, if you leave your computer alone, or if you're like a lot of other students in different departments where they use sleep mode, they close their laptop, it doesn't actually turn off. It's really easy just to plug this in. And in a more realistic sense, you would use a backdoor. So once you actually crack those passwords, you can get into it. because what the SAM file does is it stores the hashes for the computer's password, so to log on information. And the system file encrypts that SAM file, so you can't access it, which makes it a little more complicated, but I'll go through that in the next couple slides. So cracking the hashes. So once it's actually plugged in, as you can see on the top left, that is a server I have running to receive those files from the vulnerable machine. As you can see, it received the SAM file and the system file from a different machine that I have. And in the s- directory, you can see both of those files there. So now that I actually have the files, the SAM file is encrypted. So how do I get those hashes out to decrypt them? So the first thing I did is I used CHNTPW, which is a Linux tool that allows you to view and manipulate SAM files. And basically the only reason I use this is just to get the usernames, to see what accounts are actually on there and if it would be worth it. And you can see them down below. There's no actual username on this one because my micro PC that I used the rubber ducky on doesn't actually have any Windows accounts attached to it because it's a test box that I use. So next slide. So to actually get the hashes, you have to use the system file to unencrypt the SAM file, which I used in Packet, which is a toolbox with specific tools for different things. And I actually had this one pre-installed on my machine, so it's pretty easy to use the tool called Secrets Dump, which you can see through on the command line. It uses the script, it pulls in the SAM file and the system file, and that local on the end of it just tells the script use these two in conjunction. And below, you can see the usernames and their hashes. Username, their IDs, and then those hashes. And the thing about this Windows is that it uses the MD4 algorithm for hashing, which is really unsecure and old. But the reason it uses that in the first place is because that file's encrypted with the system file. So it's kind of no point in doing even more encryption when it's kind of impossible to get it in the first place. But once you get those hashes from the SAM file, you just plug them into Hashcat and it will get going and cracking, which was talked about earlier. Next slide. Which kind of comes to like as cyber professionals, how do we defend against this? So like day to day for the Wireshark thing is like just only use HTTPS websites. Uh, that Wireshark project worked only because it was an HTTP. The secure websites actually encrypt the data before sending it, so you wouldn't be able to see it in the first place. Don't connect unsecure networks that can actually do those scanning. And the main one was like never leave your computer alone because like with that rubber ducky, it takes 5 seconds of it being plugged in to install a bunch of different malware. And don't use sleep mode. I actually am part of a business major, and every single person in those classes uses sleep mode, and it's really bad. And as the next cyber professionals, as we're going into industry, we really need to make sure that the place we're working at has like a lock policy where you have to lock your computer if you're not at it, so people can't just walk up and steal those passwords. Because if they get admin access to a network, they can cause a whole bunch of problems. Implement longer password requirements. As shown before, the longer the password, the longer it takes to actually crack something. And if you're a programmer or a software engineer, use bcrypt for encrypting whatever you're doing.
All right. We don't really have anyone to ask questions, so I think that's about it.
Okay.
All right. Well
I'm gonna
done.
stop recording.
All right.